SEI website. It's a little archaic looking, but it does have current information. We keep it up to date. And then you can contact us at phillysei@gmail.com or email us directly, or me specifically directly, now that you have all my email. Um, so meet the board as usual. Everybody is contributing a bunch this year in order to set up a bunch of good presentations throughout the entire year. We almost have a full docket already. And everyone's contributing when it comes to student outreach with our Mid-Atlantic Steel Tour that I'll show 2 photos from, as well as our golf outing, and then also our student outreach event, which is a cornhole tournament that Mike is heading up. So thanks to these guys, they work hard in the background in order to make everything work. Um, so then here, I'll plug our golf outing as usual and show the sponsorships from last year. We had good turnout and we're able to generate about $2,600 to $3,000. That'll go directly towards the SEI scholarship for Philadelphia area students that are, pursuing structural engineering. So, much appreciated for all that turned out. We're going to have it in this upcoming spring as well in May. So stay tuned for information on that. And then here are 2 photos from last Friday, which apparently was Steel Day. We must have just, lucked out that it worked out this way. But we went down to Nikki Eno's Mid-Atlantic Steel, and had a tour there with about 20 students from Philadelphia area schools. So it was a good turnout. We were excited to go around and, hear about their operation there, and then also just the fabrication business that they are in. Not only do they fabricate, but they also erect steel too. So that was great. So then a few housekeeping items, just please mute yourself. Any questions, please just drop in the chat and we can moderate them and, ask Brandon at the end. And if you have any follow-up comments, you can email us at phillysei@gmail.com or, me directly. So to the topic at hand, it's structural stability and bridge construction. We are joined by Brandon Shavel from Michael Baker. Brandon has over 20 years of experience in the bridge industry with significant experience in analysis, design, fabrication, and construction of steel bridges. He earned his BSMS PhD in civil engineering from University of Pittsburgh. That's why he has those Pittsburgh bridges off to the right, his left, I think, like we were talking about when some of you came in. He's engaged in several national professional organizations, as you can see listed here. So Brandon, thank you for joining us today, and I'll hand it over to you to go through the topic.
Let me share my screen here.
Yep.
Got it? You able to see?
Yep.
Awesome. All right. Well, thank you very much, Jack, and thank you to the SEI chapter of Philadelphia for having me here today. Much appreciated. Let me go ahead and just organize my screen here real quick. So everything moved around. All right. So I'm here today to talk about structural stability during bridge construction. So why are we here? Well, over time we've had several collapses during construction. One shown here. This was in Illinois. This one was up in New York State, a tub girder bridge while the deck was being poured. I'm not exactly sure where this one is, but it's not just a steel issue. It can also be a pre-stressed concrete issue as well if certain things aren't taken into account during construction. Those 3 photos are occurrences during construction where unfortunately in a couple of cases somebody lost their life. Obviously lost the superstructure in that case too, and obviously all things we don't want to deal with. This last one that over down on the right is one that was a collapse that occurred during demolition, actually, which can also be a critical stage during the bridge's service life, taking a bridge out of service and taking the deck off and removing pieces and parts of the bridge. So these issues occur. They don't occur frequently, but every now and then they do. And as engineers, typically we design the structure, and we put it on plans and we ship it off. It gets bid and built, right? But what goes into building that bridge? What are some things that, as design engineers, we need to be cognizant of as we are reviewing maybe erection plans, maybe erection calculations, maybe contractor submittals and things along those lines. So the goal here today is what I want to do is I want to kind of run through this outline. I'm going to share some references and guidelines. We'll talk about some critical stages of bridge construction. Obviously, I think we can all think that the bridge during construction is not the same bridge that we have as final design, right? In many cases, there's stability concerns during steel or pre-stressed concrete erection, during girder erection, that the contractor engineers need to understand and take into account. Obviously, wind loading is a lot different from a structure that's not complete versus one that is. Various non-composite conditions that occur, constructability, deck pours, things like that. We'll talk a little bit about stability considerations, kind of going back to what the critical stages are and how we can investigate those as a construction engineer, or maybe what we should be looking for. And then also, talk a little bit about what probably needs to show up on erection plans and procedures and calculations. Not every bridge is going to fit into this. Some of your simple bridges, some of your simple, maybe single span bridges or short span bridges, they don't all fit into, all of this, right? Some of them are a little easier, we'll say, to erect than others. And then we'll kind of summarize everything up. And I will touch on bridge demolition a little bit as well. I think what I want to do is first start with some references and guidelines that are out there. So I've been lucky enough to both be a part of some of the development of some of these, but also work as a engineer developing steel erection sequences and construction sequences for contractors. So I've got some professional experience in that background, but then also some experience helping in the development or review of some of these guidelines. And these are three that if you're involved with construction engineering, these are three you definitely want. There are some others with regard to wind loading and things along those lines, but these are the three big ones. The first one is the engineering for structural stability and bridge construction. This is a National Highway Institute course, course number 130102. So, and I'm actually lucky enough to be one of the instructors for this course, and have been able to present it at a few locations over time. It's a really good resource. You obviously get this manual if you take the class, which I'll talk about in a second, but it's also available at the FHWA Office of Bridges and Structures website as well. So if you're interested in finding it, you could just type in the title, throw FHWA in front of it in your favorite search engine, and it should take you right to it. The one in the middle is dedicated to steel bridges. It's an AASHTO, National Steel Bridge Alliance collaboration guideline document. Actually, it's a specification, Steel Bridge Erection Guide specification. It's what we call the S10.1 document. And this has a lot of good information on what you should be looking for, what you should be checking, the checks you should do, what needs to show up on erection plans and procedures for steel bridges. And then the one over on the right is a PCI document with regard to lateral stability of precast and pre-stressed concrete bridge girders, which is really one of the major states and major things that need to be considered for I girders during during concrete girder bridge erection. So the nice thing about all these documents are free. I think you might have to pay for the PCI one if you want a hard copy, maybe unless you're a member. But the PDF is free, so you can join that and download that. But the other ones are free. Again, at the FHWA website, the AASHTO NSBA one is available at the NSBA website, and the PCI one obviously available at the PCI website. Again, all really good references when dealing with construction engineering for all these bridge types. I'm going to put a plug in here for this National Highway Institute course, the 130102. That is the Engineering for Structural Stability and Bridge Construction. It's a 2.5-day course. You can find out more at the NHI website. Anybody can host it. Typically DOTs will host it and then allow some consultants to attend, but it's not out of the realm of having a consultant host it and having some of their friends come too. Yeah, there is a cost associated with it, of course, and there's your own labor cost associated with it as well. But if you're involved in construction engineering, if you're working on that, this is a must. Um, what you're going to see here today in the slides that I share a little bit later are a few very quick excerpts of the class of the course, just to kind of wet your whistle a little bit with regard to what's in the course, and then some other things from my personal experiences over time as well. So so just keep that in mind. This is the 30,000 foot flyover of all of this. There's definitely a lot more that goes into the construction engineering for girder bridges. So let's just walk through what some critical stages of bridge construction. This is just a typical two-span bridge. This one's going to be steel. It could be concrete as well. Obviously, a little bit different if it's a pre-stressed bridge. But let's just kind of walk through what occurs on a construction project. Something like this, just a girder bridge. We're going to have some kind of it's a two-span bridge. We're going to have the pier constructed, the abutments constructed. We're going to have some kind of shoring tower in the middle, a lifting crane, the big crane shown there in there. And, we'll go ahead and place that first girder. Now there's there's some considerations that need to be taken into account with that first girder. If I just put it down without any bracing, if a little bit of wind comes, it's just going to blow the thing over, right? So we at least have to have some type of lateral bracing, temporary stability brace at the supports. So you can see that identified there at the shoring tower, but then also back at the abutment as well. What else do we need to worry about? Well, this is a very long unbraced length, right? So we have issues with lateral torsional buckling capacity. During construction, we often have long unbraced lengths that need to be considered. But another component is also wind. I mean, I can't just necessarily put that girder down and hope for the best, right? There's going to be some kind of wind load that needs to be taken into account. Is it a 70-mile-an-hour wind? Is it a 30-mile-an-hour wind? Can the contractor only work when the winds are less than 20 miles an hour? Those are things we look at as a construction engineer. An engineer working for a contractor will say, there may be some certain limitations with regard to that wind load when they can place girders, and that all needs to be considered and thought of by the engineer working for the contractor. So we'll move on. We'll go ahead and put our second girder down. This particular one has cross frames on girder 2 on both sides. That'll often occur. They'll lift the second girder in with several of the cross frames attached. In some cases, it may be all the cross frames. In some cases, the contractor may choose to, for the sake of speed and time, may choose to not put in all the cross frames. And if you think about the cross frames getting put in there, there's bolting that occurs, there's fit up that occurs. There's no reason to have the big crane sitting there holding that girder while we put in every single bolt on every single cross frame, right? So there may be opportunities to move forward with another girder and not necessarily erect all the cross frames. So the contractor may want to do that and come in with a smaller, even a man lift or a smaller crane to erect those other cross frames later on. So you may see something where they're only putting in half the cross frames in the bridge, or maybe every third one. Hopefully their engineers run some calculations to show that's permissible under steel self weight. So you may not always see all the cross frames erected all at the same time. The big crane costs a lot more money than some small mobile crane, or even a man lift that may be used to erect those cross frames. So just marching ahead, kind of just continue on erecting all those girders up into that shoring tower, right? Typically, that's how an erection process will work. Because that big crane that we saw earlier, that's going to stay in one spot typically and be able to lift all those girders into place, and then maybe move down the span or move down the longitudinal length of the bridge to the next spot. So in this particular one, 6 girders are in the cross section. It's there could be 10, there could be 4, right? Just for illustrative purposes. Then we'll often march ahead to the next spot and go with the next field section. A lot of times it's easier to erect continuous lines, like keep going, field section all the way across, and then all the way marching down the bridge, rather than having drop-in sections. Drop-in sections can often lead to some challenges with regard to lining up field splices and things like that. So this particular erection sequence just assumes we're marching down the length of the bridge. But you can see we put that next girder in, we connect the field splice, it sits on the pier on a bearing, but we also have that temporary stability bracing there again at the pier. Again, we need some kind of brace point there at the pier to make our equations effective for lateral torsional buckling. In this particular case, not only do you have like a long unbraced length from near that field splice to the pier, but you got a pretty hefty cantilever hanging out there too that often needs to be checked. It's probably not going to control, but things to be concerned about in that particular case are where is the girder deflecting to? Is it twisting? Is it deflected downward too much where I won't be able to make the next field splice? Often it'll be okay for stability purposes, for stresses and things like that, but deflection control and consideration of deflection is always something to consider as well during erection, steel erection. Then again, marching across the bridge, working our way across, erect all those girders, maybe all the cross frames, maybe not all the cross frames. This particular detail or sketch here shows all of the cross frames. So things to consider there again. Again, we have to think about wind. It's not a completed structure, right? The wind, it's really blowing on one span with a little bit of a cantilever, right? So there's things to consider with regard to that. And one thing I'll mention here is often what I would see is some calculations show, that there's no, all your wind is blowing laterally on the bridge. It's really just a collection of the IYs of the girders that are resisting that. Because you don't have any lateral bracing, top flange or bottom flange, there's really like no AD squared term with regard to the stiffness of the whole entire cross section. So you're really just relying on 6 times IY to resist that wind load. So just keep that in mind when you're doing analyses for these, or you're checking these, or looking over some erection calculations. That it's really just the IYs. Unless you have lateral bracing, then that changes the game a little bit. But we have to consider wind here, and it's not just necessarily consider wind for strength purposes, but also deflection purposes. I mean, we're going to have people out there working on the bridge. They may be setting rebar, perhaps, and if the bridge is deflecting, 4 or 5 feet in one direction, which it can do, if it's not stiff enough, we could have some issues with that, right? Some comfortability issues, as we'll say. So. Then the steel erection would continue on. Place that last girder down, connect the field splice, place it on the north abutment shown there, and then again, braced at the support, braced at the north abutment. Again, this is another consideration where we have to think about wind. We have to think about that long unbraced length of that girder. Is it gonna survive our lateral torsional buckling capacity checks and things along those lines? And then just march along again, finish out the girders. And we have a completed steel superstructure in this particular case, right? We removed the shoring tower. I should go back here. Typically, you'll see that the shoring tower would get removed after those, when we're at this stage, actually. That is so that the field splice tips at the end there, they actually deflect upward, which makes the construction and the connection of this next piece much easier. You can think about bringing that girder piece in and connecting it to something that's pointed up as opposed to connected to something pointed down, especially when trying to set it on the north abutment. So often you'll see that shoring tower get removed once the span is done to kick those field splice locations upward. And again, one thing we obviously have to consider here is again the wind loading on the completed steel framing. And again, like I said, it's a collection of the IYs, a summation of the IYs that are generally resisting that lateral deflection, right? And what can my bearings take? We always design for the final composite condition, but in some cases, again, the non-composite condition can control. And maybe again, not so much for strength, but we'll say serviceability during construction, and the wind and the amount that those girders may move for wind load applications is something we do want to consider, and maybe not necessarily neglect when we're designing this, okay, as a design engineer, we might want to look at wind on the completed steel superstructure just to make sure we feel good about it, right? And we're not going to have major fluctuations and deflections and things like that. Of course, once all the steel is up, or yeah, my focus, of course, is gonna be on steel for a lot of this. Once all the steel is up, we have to place the deck, right? We have to place the concrete deck, and there are certain things we need to consider. Generally, these get considered as part of our constructability checks that we do as a designer. But the contractor often goes through these as well, just to get a better feel, make sure they're good with the deck pour sequence that may be shown on the plans. Yeah, as the contractor's engineer, sometimes I may have to look at this and make sure everything's good. You could think about think about this. We're loading a lot of wet concrete on the bridge in the non-composite condition. So that changes the game a little bit, right? We've got this pretty heavy load, the concrete deck, going on just plain steel or bare steel. And there's certain considerations for that, right? We're in a non-composite condition. Again, we're concerned about, in most cases, the top flange and compression. And is that going to survive? Is that going to pass the lateral torsional buckling capacity checks, lateral torsional buckling resistance checks we have in the AASHTO LRFD. There's a whole section there on constructability, and it really has to do with the deck pour. And loading the bridge in pieces and parts like this with regard to the deck and the various staging is often cases the most critical condition with regard to constructability. You really have to take a look at that deck pour sequence and make sure that the girders will survive that. The girders will pass the mustard, we'll say, for that, because the loading in this particular condition is quite different from just assuming a monolithic pour and putting all the self weight of the wet concrete on. So it's pretty important we do look at the deck pour sequence, especially when you get to some longer span composite steel girder bridges. In addition, our exterior girders, we have to consider the flange lateral bending effects caused by the deck overhang brackets, and AASHTO LRFD addresses this as well. Those overhang brackets, as shown, I have a picture. We can kind of make them out sitting on the girder there, on the exterior girder. We have to check those forces that are getting applied to the girder. We're going to have those overhang brackets spaced at, say, every 3 feet, maybe in some case 4 feet. In some states, that overhang bracket also supports the bidwell machine or the screed that's going to place the deck. So that's another load that's acting on that overhang bracket. That is, you can just think of the free body diagram over here on the left. That's pulling on the top flange and pushing on the bottom flange. We're going to impart some sort of lateral loads on that top flange or on the bottom flange too. The cross frames or the diaphragms, those are going to be what's going to resist that lateral load. So you can imagine, you basically have a beam on multiple supports, right, in that lateral direction, resisting these loads. We have the weight of the wet concrete out there on the overhang. We have the weight of the formwork. We have the weight of people out there, and then of course the screed rail. If you're in one of the states that puts the screed rail out there at the edge of the deck as well. So all these play into the loading on that flange. And because that top flange is in compression, we have a lateral bending stress that gets added to that with the 1/3 rule that's in there in the AASHTO LRFD. So it can add up, right? And really in the lateral direction, again, it's really just a simple consideration of a beam on multiple supports. So you can go to the AISC manual and pick out the beams that are on multiple supports and come up with what those moments are. There's also in the AASHTO LRFD, there's some simplified equations in the commentary that talks about the overhang brackets and the loads that get put on them. But again, these two things, the deck pour sequence and these overhang brackets and the loads they impart on the flanges, those really should be considered by us as the design engineers when we're walking through the design calculations and checking the constructability. It is making sure that the bridge is indeed constructible for the deck pour sequence that we do specify. You can make some simplifying assumptions here. You can be a little conservative. I always tended not to get right down to yeah, right down to the, you know, the tip of what I can do here. So take some conservative approaches with maybe some of the loads, and just, you know, if you have multiple cross frame spacings, just assume the maximum cross frame spacing. You know, it's not going to change things that much at the end of the day. You want to make sure the bridge is constructible, and you'll see that in most cases it is. Of course, narrow flanges are typically not good for this. Real small flanges, you know, and typically in the positive moment region, we do have smaller flanges. If you get down real narrow, yeah, hey, it works great for strength. You may find it may not work so well for the constructability check. So just something to keep in mind going forward. All of that I discussed before, you know, we have all of that's in the non-composite conditions, right? So it's vastly different from when we're just plug into our program that we might want to use and say, all right, run the live load on it. Let's see what happens. Okay, we always need to take that step back. If your particular program you're not using doesn't look at constructability, you really need to look at some checks outside of that program if you're using a program to design your girders for that. So just keep all of that in mind, the importance of looking at the deck pour sequence with that. So let's talk about some stability considerations. You know, in the previous couple slides, I talked about you know, some conditions where, you know, we have concerns with unbraced lengths, typically for single girder stability of steel girders, two girder stability of steel girders, and then we'll talk a little bit about on the pre-stressed concrete side and some things that we need to consider there as well. We could have similar issues, not necessarily with regard to lateral torsional buckling, but yeah, with regard to roll stability and lifting stability of those types of members. So as I mentioned before, you know, long unbraced lengths, you know, as we know, they affect the torsional buckling resistance. You know, up over in the top left there, I have a figure that shows, you know, that's kind of our as designed, we'll say, unbraced length. You know, typically 25 feet, something along those lines, right? You know, our cross frames are going to be spaced maybe 20 feet, 25 feet. You know, that's great for the final condition, right? But during steel erection, you know, that unbraced length is going to be much larger. So all of a sudden, our unbraced length is maybe 50 feet, maybe 100 feet, maybe 125 feet in that particular case, right? Yeah, however many 25-foot spaces there are. Sure, our loads are not the same as in that final condition, right? Yeah, as in this unbraced length, you know, it's just steel self weight. But you'll find as you get out to these longer unbraced lengths, your structural resistance, your lateral torsional buckling resistance goes down significantly. Okay, and just show here, you know, a finite element model around the left, just kind of showing, you know, here's, you know, lateral torsional buckling of a section because of a long unbraced length. And really that unbraced length is from cross frame to cross frame at the end of the day, unless you have some other kind of transversely supporting mechanism to provide a brace point. All right. So yeah, those are the concerns with regard to single girder. So what do we typically do? You know, we're concerned about the lateral torsional buckling resistance of the girder. If you're familiar, you know, with the AASHTO LRFD, you know, there's a nice section there on lateral torsional buckling, section 610.823, and we have three equations there. And it's really those equations over on the left, you know, the one number 2 there looks pretty meaty, right? Pretty big, pretty ugly looking. But really, it's those equations are just an interpolation of this graph over on the right. You know, basically, as we get longer unbraced lengths, we move down, we move along the graph out to the right here. As we get longer unbraced lengths, our resistance is going to go down. Well, that kind of makes sense, right? So these equations that are in AASHTO, the -1, the -2, and the -3, are really just you know, form fitting this graph at the end of the day. You know, we go from our compact section to our non-compact to our slender, our slender sections. Okay. The first equation goes, you know, goes from 0 unbraced length to the first anchor point. That first anchor point is that LP in this particular case. So our length that gets us to LP. Okay. If our unbraced length is less than LP, then we can use equation 1. If we're in between LP and LR, as shown in AASHTO, you know, we now have basically the equation number 2 there that is really an interpolation between anchor point 1 and anchor point 2. And then if our umbrace length is greater than LR, which we typically are during steel construction because we have these long umbrace lengths, we're down into that third part of the equation. So you can just see, again, as our umbrace length gets larger and larger, our resistance goes down and then kind of really tanks exponentially, we'll say, a little bit towards the end there. So just so that's really what we want to be looking at when we have these long umbrace lengths. Come into the AASHTO LRFD, looking at these. Now, you could run your own analysis. You can run your eigenvalue analysis and all that, which actually what was on the slide there that I showed before. But you got to be careful with some of that with regard to your boundary conditions, how the girders are braced and everything. It's always probably good to come back to these equations, take a look here, and then maybe run that analysis and make sure you're kind of in the same ballpark with regard to that. So say I do have these long umbrace lengths. What can I do to make my girder work? I'm stuck at 125 feet or 100 feet. We'll say, this is what we want to do. We can't put we have to erect this first girder and that's that, right? So maybe I use a hold crane to reduce the bending moment of the girder. Maybe I can maybe I have a smaller crane on site that the contractors determine they're going to have there. And I'm going to hold the crane at midspan. I'm going to reduce the moment, right? Instead of a nice, big moment diagram, I'm going to put a point right in the middle and pull the girder up a little bit. So my moments are significantly reduced. The big thing there, the hold crane cannot be considered a brace point. And that's something to keep in mind. There's not enough lateral stiffness typically with that crane holding it there that you can consider that a brace point. So it's probably a wise decision to not consider it a brace point. Okay. Second thing you could do, or another thing you could do, is you could provide a brace point at the midspan, maybe with some tie downs. Maybe you've seen this before. Cables wrapped around the girder down to like a concrete deadman or a big concrete block down on the ground, both directions on both flanges, and just to use to brace the girder. Those would be attached obviously before the lifting crane releases the girder. And that would provide, you'd have to do some design calculations, of course, but that would, assuming your calculations are correct, that could be used to provide a brace point at the midspan and reduce your umbrace length, cut it in half. Or maybe you can just provide more temporary support, different shoring towers, a different shoring tower arrangement, and then put that lateral brace down to that shoring tower. Again, long umbrace lengths, as I said, they affect the torsional buckling resistance. Don't just walk away once you get the second girder up. You got to check that. Maybe you're only going to have one cross frame at midspan. You need to make sure that works in this particular case as well. Maybe the contractor wants to come in and just put in one cross frame initially and then come back in and put all the rest later. So you have to look for these long umbrace lengths, not just for, vertical load, self weight, but, some considerations with regard to wind as well. Okay. So let's move on to two girder stability. There are some conditions where you do have two girders erected, like in that previous slide, where I might have some issues with regard to stability of narrow units. The designer typically uses the umbrace length LB for girder buckling. That's the distance between cross frames. But we've seen girder systems as a whole, a narrow, long and narrow girder system, so a long length to width ratio, that they become susceptible to a system mode of buckling or a global stability mode of buckling. In this particular case, you could put all the cross frames in you want. That they're really not going to affect the behavior of the bridge, and that's in the system mode of buckling. And this really came to light in 2002, and I shared this picture before. This is a Marcy, New York pedestrian bridge. It consisted of single box girder with no top lateral truss system, so no lateral bracing in the plane of the top flanges. The girder did have internal K-frames spaced at a little more closely than normal. But what research found, University of Texas at Austin, Joe Ura and Todd Helwig that looked at this pretty extensively over time. What they found is that this particular girder really behaves similar to a twin eye girder system with no lateral bracing in between. And it really started some concerns with regard to structures like this. What occurred here in the Marcy Bridge is, they got the steel up, no problem, got the rebar laid down for the deck, and they started pouring the deck. And once they started pouring the deck and got out, maybe I think a third of the way out, the girder twisted globally and unfortunately fell down. And I believe at least one of the workers has died on the job there. So So what was found is, the cross section wasn't offering enough global stability at the end of the day. So, a lot of investigation went into this. You can think about this for a two girder system, your LB, your unbraced length between cross frames, versus LG, basically the length of the global system. And you have buckling in two different modes here. One is lateral torsional buckling between the cross frames, and then one is a global buckling for the entire bridge. And some studies done at UT Austin, you can put the same bridge in there with the same girders and the same cross frames. You can see the over on the left, the global buckling critical moment is roughly 800 kip foot. And over on the right, you can see the buckling between cross frames is close to 1400 kip foot. So almost half, right, of that. So something to consider if you have a two girder system, if you have a long two girder system that you're putting a deck on for some reason, maybe even some three girder systems as well. And this gets talked about in the AASHTO LRFD equation 610.34.2. A lot of numbers there, -1. This whole section talks about the global buckling of narrow systems. And really, there's a lot of this equation was developed, through the research work based on the Marcy Bridge collapse at UT Austin. And I'm not going to run through all the things here, but it's really just some general parameters that you can easily come up with based on your girder design, based on your cross section design. You can see CBS there is either 1.1 or 2.0, depending on whether you're simply supported or continuous spans. Okay. I effective really comes down to your effective IY basically at the end of the day. It's you got your IY on the compression flange and your IY on the tension flange, and you're really that's really a combination of those two, and just where the centroid lies within the girder. There's a statement in there for non-prismatic girder properties. AASHTO recommends, doing some kind of weighted average for IX and I effective, so you're not looking at each individual location along the girder. You make some engineering judgments with regard to that. A weighted average is fine. A lot of this is already approximate, so being a little more approximate is not going to change anything. So you calculate that global stability moment, and really what AASHTO says to do is, you're considering all the girders across the width of the unit and the span. You're going to take your total factored moment for the deck placement, and it shouldn't exceed 70% of that MGS, the global stability moment. Okay. And really that's a really big thing for pouring the decks on long narrow systems. So big length to width ratios. All right, think a long 200 maybe 300 foot spans that maybe only have 4 or 5 girders. This really starts to play a role regardless of how many girders you have in the cross sections. So what happens if you don't meet that? What happens if your moment for your deck pour is greater than that 70% of the MGS? Well, you may want to start considering adding flange level lateral bracing, so typically in the top flange. You could try to revise the unit system stiffness. Maybe you do a higher end analysis and look at the amplified girder second order displacements and verify they're within some tolerance. You can look at the buckling. You can do an eigenvalue value buckling analysis and get into all that. But generally, this equation is gonna serve you well in those types of conditions. So just an example here. Don't necessarily get caught up in the numbers, but really want to show here's this two girder unit. We have a simple span, a length of 180 feet. All right, and we're going to do a couple different things here with it. Again, we're going to look at bridge 1 and 2. They have no lateral bracing. All right, bridge 1 and 2, 180 feet. Bridge 3 has some lateral bracing just in the last 2 bays on each side, if you can make that out there. So basically our effective LG in that case is only is 1,200 inches as opposed to 2,160 inches, and everything's converted to inches here, okay? So you can think of, we've narrowed down that global unbraced length, we'll say, or that global length with regard to stability that we're concerned about. Bridges 1 and 3 have the same cross section shown there over on the left. So they have an IY at 2,000 and an IX of 100,000. Bridge 2 is a bigger has bigger flanges, more stout, bigger IX, bigger IY. All right. So we're going to compare bridge 1 and bridge 2, right? And we're going to compare bridge 1 and bridge 3, right? Bridge 1 and bridge 2 is the same bridge, just with bigger girders. On bridge 2, bridge 1 and 3 are the same girders with some lateral bracing at the end bays. So you could run through these calculations. I'm not going to run through them all here. It's math. It's kind of plugging things in, right? But you can walk through bridge 1. We get an MGS of about 10,000 kip foot. Bridge 2, I'm going to have a slide that compares all these in a second. Bridge 2, 17,000. Bridge 3, where we have that shorter effective length, we'll say, for global stability, we're up to 31,000. So let's put all these on one slide and multiply them by 0.7. Okay. So you can see, bridge 1, again, I have that one girder section, the same girder section as girder as bridge 3. I have roughly 7,000 kip foot. And we had a global moment of 8,600 kip foot, right? Does it pass? No. Okay. That's the MU there. Well, really what I want you to focus on is how the capacity or the resistance changes in this particular case. So bridge 1, again, no lateral bracing, the smaller flanges. So let's say we go from bridge 1 to bridge 2, same framing plan, right? We made the stiffness a little bit bigger. We made our IY almost double. We 50 increased our IX by 50%, but not a whole lot of gain on the capacity or on the resistance for global stability, right? We went from 7,000 to 12,000. Some gain. It does work, right? But we got a pretty big section there. Maybe we can't get that section to work for some other reason, right? Bridge 3, compare that to bridge 1. All right, there we just added in some top flange lateral bracing in the two end bays. You can see the gain we got in our global stability moment. We're up to 21,000 as opposed to 7,000. So throwing in a little bit of lateral bracing, right? Just in the end bays, the two end bays on each side helps tremendously with regard to that global stability. So, so if you're in a design and you're having issues in this regard, you really want to start considering, I think, lateral bracing, especially spans greater than 250 feet. Really take a look at this, and you don't need it full length. A couple of bays at each support, either direction, should suffice, and you can run through these calculations and see that. Not to be left out, we do have some issues with regard to pre-stress girders during construction, and it really amounts to the roll stability of these. Initial girder rotation gets compounded by maybe there's some lack of flatness on the bottom flange of the beam. The bearings are a little bit more flexible for these. A lot of times we're putting these on elastomeric bearings. So if you get a little on a plumbness of the beam, maybe you get a little more roll on the elastomeric bearings. It kind of all adds up, leading to some increased girder rotation at the end of the day. And in some cases, maybe too much, and we end up with a condition kind of shown over there on the right. Precast girders, during erection before deck slab, again, they're vulnerable, just like steel eye girders, but maybe a little bit different, right? We in some cases we have simply supported conditions, and maybe we were making them continuous for live load, right? The deck isn't poured yet. We don't have any composite action going on and relying on that deck. We don't have the continuous lateral support in the lateral direction that the deck slab provides for us. And as I said, the elastomeric bearings do allow some rotation about both axes. The influence of roll stability, what are some influencers? Again, the bearing slope, maybe you're on a curve for some reason, and you have some kind of sole plates that may be beveled or something, and you have that acting against you in this particular case. Bearing skew can play an effect. Of course, there's always going to be girder imperfections, no matter what kind of girder we have, right? And that'll play a role. The rollover control stability. It's not a lateral torsional buckling mode, all right, like on steel girders. The girders, the flanges are so big on a pre-stressed beam, right? We want to make sure they're not going to crack under self weight, and that could lead to issues. So how do we check this? Well, as I said before, there's a PCI guideline shown there on the right that goes into all these. I'm not going to get into all these equations. It's math. They're all laid out there in the PCI document. But there's factors of safety against cracking during construction. Factors of safety, the safety factor you want to compute against rollover during construction. But then also we want to check the lateral deflection of the girder and make sure we're okay with that, and that feeds into some of these equations as well. You can see the Z0 terms right down in the bottom in the denominator, and that's where this comes from. So it's a lot of math, some big ugly equations that easily programmable into a spreadsheet. But it's all laid out here on the checks that we want to do to make sure we're good and we don't have any issues with the pre-stress girder. Again, the tilt angle as well. Another calculation. Everything's given. It's all based on parameters that you've already designed for or already have from your design. So just a lot of usage of those parameters in various equations. Again, if you're looking at this, if you're doing construction engineering with pre-stressed girders, again, you really need to take a look at the PCI guideline here for lateral stability. What are some methods to avoid stability issues? Well, again, pretty similar in some cases to steel eye girders. Maybe you want to increase the bottom flange width, bearing pad width. Maybe you don't want a real small bearing there on a really big girder. You really want to brace the girders at the supports during erection. That may help out a lot. The top flange brace down to the abutment and the pier seats, brace the girders to each other. Some configuration shown here, using the face of the pier, the face of the abutment, and having some bracing members, some solid bracing members to provide the necessary stability that you need here. Maybe it's from one side, maybe it's from both sides. Maybe you're tensioning them down, maybe there's tension and compression in these members. So things that we need to think through. So let's just briefly talk about bridge erection plans and procedures, and we'll just kind of touch on some bridge demo things as well. The erection plans and procedures, the general objectives, they really need to convey the means and methods of the particular erection sequence to the field staff. This is how the field staff out in the field is going to build the bridge. There's always logistical issues, multiple subcontractors working on a site, so the sequencing and the coordination is critical, really, and making sure certain trades don't conflict with each other. I can get girders in at a certain time, get them erected at a certain time. And really, the structure, can be and often is its most vulnerable in its most vulnerable condition because it's not yet fully assembled and braced. We're lifting girders, we're putting girders down on long supports that are a lot longer away from each other without any bracing. And as we kind of talked about before with my first few slides, those are some vulnerable conditions that we really need to take into account. The erection plans and procedures, there should be, the plans, the procedures, step-by-step methods on how to go about and build things. There really needs to be some calculations that support them as well, okay? But at a minimum, the plans, they need to show a sketch of the work area, some site logistics. Maybe there's a river in the way, maybe there's a feature that's being crossed, a highway, something else. The sequence of erection, do I start from one abutment to the other, or go from one direction to the other? Pick weights are often useful. Make sure that. Often you'll see some crane charts provided in there as well. And often much more with regard to that. The plans are going to describe the detailed means and methods, including temporary works. They really need to be job specific. Make sure the loads equal the resistances of its various temporary shoring towers, bracing components. Maybe there's tie downs, things like that. Those plans and procedures, they need to be based on the contract drawings and the specifications. Make your state specifications, your owner specifications. Shop drawings. Make sure nothing's changed with regard to shop drawings. And of course, as I said before, there needs to be some calculations prepared by the contractor, by the engineer working for the contractor that support all of this too. It just can't be willy-nilly. Just how we're going to build the bridge. All right. Where can you find guidance on erection plan submittals? Again, maybe Pennsylvania, of course, may have some state-specific or owner-specified submittal guidelines. Maybe some specific contract documents as well. There's the AASHTO and SBA Steel Bridge collaborations, Steel Bridge Erection Guide specs. Appendix B of NCHRP Report 725 really led to a lot of what's in that guide specification from the AASHTO and SBA, but there's far more detail in there. There's some really good recommendations in the reference manual for the NHI course as well that I talked about before, the course 130, 102. And that has really good details with regard to what you should be looking for, what you should be looking for as an engineer working for a contractor, and then maybe on the review side as well, if those erection plans are submitted for review. And then, of course, if we're working over railroads, they may have some requirements as well, adjacent facilities. But really, what goes into it? Well, what I'm going to share here is an erection plan for a curb girder bridge that I've worked on before. Generally, you're going to start off with just kind of showing, step by step, an overview of each stage of construction, and you can just kind of walk through it here. As you march along the length of the bridge, we're going to erect these girder segments, these cross frames with these cranes. You're going to have some lifting cranes there. We're going to have some holding cranes there. Where do I need, in the ballpark, where do I need to position the lifting crane? Just an overall schematic of the whole procedure while building that bridge. But then you're going to have some detail sheets, or you should have some detail sheets that go down to the nitty gritty of each stage, right? And I have four boxes, kind of highlighted here that have the different various items that really need to be shown or should be shown, especially on a curved girder bridge project, a curved steel girder bridge project. You want to show a plan view of the erection stage. Where are the crane locations? Where are the temporary supports? Where are the girders and assembly for each stage? What girders and pieces and parts make up that assembly? Is it all the cross frames? In this particular case, we erected all the cross frames as we marched along the length of the bridge, so that's why they're all shown. Okay, maybe you're skipping a bunch of cross frames, and that would be shown here. So, laid out schematically, typically in plan view, showing all those things. Should be a written procedure, almost kind of like the instructions to building an IKEA dresser, we'll say, right? Just describe each stage, right? Word by word, enough information there. Provide the order. Am I going inside girder to outside girder, girder 1 to girder 4? When am I using a holding crane? When can I let that holding crane go? When am I using temporary supports? How many bolts do I have to put in the field splice? Typically, we're gonna put bolts and pins up to 50% of the holes. Maybe there's something else going on where we're having a limited amount. Again, all of that needs to be identified within that written procedure, or should be identified in that written procedure. I'm also going to show crane information. The contractors, engineers shouldn't work in a closed box. Really should be communicating a lot with the contractor with regard to what kind of cranes they're going to be using on the job site, what cranes they plan on using, and maybe some alternatives. What are the types? What are the lifting beams in this particular case that are going to be used? And then a table of pick weights, particular crane radii that are permissible, and the crane capacities. And then general notes for the stage. You heard me talk about before, maybe there's some wind velocity considerations. Maybe I can only have wind at a certain speed for various stages of construction. Cross-frame bolt installation or even cross-frame installation requirements need to be provided, and the minimum bolting requirements as well. Maybe I'm not going to put in all the bolts on each cross-frame. I'm only going to put in 50%. Maybe I have to put in 75% for some reason. So keep that in mind, and that's really what should be shown. And then, other details, right? Specific details. In this particular case, we had a hold down at the temporary support. We utilized one single temporary support tower under one girder, and we braced that girder up at the top. You can kind of see the tie downs shown there. And then on another sheet, which I don't have here, it kind of shows those anchorages, those ties coming down to the concrete deadman, the concrete blocks on the ground to provide that brace point. There's certain calculations that have to go into making sure that's a sufficient brace point. As I said, there should be calculations that support that erection plan. A lot of things shown here. The calculations need to address all the critical stages, verify the structural capacity and stability of the girders at each stage, take a look at wind loads, take a look at all the various loadings that may occur, look at member deformations. That's really more so helping out your contractor, making sure I don't have conditions where the girders are maybe sagging down at the field splice tips and making connection with the next piece virtually impossible. I'm not going to walk through all of these, but they're all discussed in great detail in the guide specification from the AASHTO NSBA S10, and then also in the NHI course as well. I did want to spend 1 minute or two on deck slab removal. Demolition can be a pretty critical item when taking apart a bridge, taking a bridge out of service. Why is that? Well, we're often loading the bridge with some kind of excavator, some kind of device to remove the concrete slabs. We're saw cutting the slabs. We have a non-composite condition for some of the girders while backing that while backing the concrete deck off. All right, so we have a different loading on, while the loading may be almost the same as an HL93, in some cases it will be more. These excavators weigh a lot more in some cases. We have some non-composite conditions on the bridge at certain stages as well. So really need to start thinking about that. We know where the excavator is going to be. We know what deck slabs we're removing. Are those girders sufficient for that non-composite condition? Something to be looking for on, especially longer spans, removing the deck, and make sure that that's being done by the contractor as well. One critical item that we've seen is when you have in-span hinges, or which are sometimes referred to as shelf or shiplap joints too. And I'll show that on the next slide. This is some photos off the internet. Condition that we had down in Cincinnati, where we had the center span was sitting. We had the end spans come out and cantilever beyond the piers, and then the center span set on that. The contractor was removing the deck from the end span, and then progressing along, removing the deck from the center span, and we had a collapse, unfortunately here. And really, what it did is it pulled the girders up from the end span and kind of brought them all over to the other side of the pier. You can see in the photo over here on the right, there's a pile of girders actually laying right next to the pier here, because they kind of probably flipped up and over that pier. What happened there? Well, my pretty graphic shown here. We removed the deck from the deck was removed from that end span. You kind of lost some counterbalance behavior, we'll say, from that load in that end span, and we put a lot of load out in that center span, and it just put too much load. There's no force in that end span resisting all that weight out in the center span because of those shelf joints, those shiplap joints. We had bearings there between the girders, and really just caused an uplift condition over on the end, and obviously too much uplift that couldn't be restrained by the deck that was there. So in some cases, demolition can be just as important as steel construction, and needs to be given its due consideration by a contractor and the contractor's engineer. So that kind of summarizes what I want to share today. Again, it's a 30,000 foot overview. We spent some time talking about some critical stages of bridge construction. Really got hammered away on stability and wind loadings during construction. The non-composite conditions that we have that are not the same as our final design bridge. Talked about stability considerations, maybe opened your eyes maybe to 2 girder stability or even 3 girder stability during deck construction. Some issues that we really need to consider with regard to steel construction. In some cases, when you have long narrow systems without any deck, you may want to consider that as well. We talked about our pre-stressed girders also have some roll stability concerns that we need to be considering as well before the deck is placed. Spent some time with the erection plans and procedures. Talked about maybe some things to look for as a review engineer, or things as a design engineer that you want to consider as well. Really, again, I can't stress these enough. If you're involved, if you're doing work for a contractor, if you're reviewing the work by a contractor's engineer, these are 3 really important documents that you want to have at your disposal, and really want to take a look at. And again, I'll put in one last plug again. NHI has a really great course for this. If you're interested, check out the NHI website, see when it's offered. Maybe start thinking about maybe you want to have a group sign up for it and get enough folks there, get enough folks for that. So I really appreciate the time here today. I'm happy to answer any questions, or attempt to answer any questions that folks may have. And again, really appreciative of your time here today, and being able to talk about this issue, talk about some construction issues during bridge erection. So.
Well,
Jack, I'll turn it back over to you.
Thank you, Brandon. I appreciate it. So if anybody has any questions, please drop it in the chat. I had a question just off the cuff when we were looking at the bridge demo recommendations. Are they included in any of the references that you mentioned here?
Yeah, very lightly. In the NHI course, we talk about it a little bit, so there's some information there. More so with regard to taking the deck off a continuous span unit, and not necessarily the hinges, when you have hinges and stuff like that. But yeah, it's kind of the reverse construction, right? So there's some good information in the IHI course. I think we talk about it even more briefly in the AASHTO and SBA document, and I can't say with regard to any of the pre-stressed concrete, but yeah. So I mean, it's not talked about a whole bunch. And there's I believe there's a ASCE group led by a gentleman from Genesis Structures who does a lot of that work, and I think they may be developing something soon for demo bridge demolition and considerations for bridge demolition. So
Okay, great. Well, I'll share my screen quickly to kind of outro us here. I don't see any more questions in the chat.
okay.
Oh, yep. So, thank you to Brandon for joining us today. We're going to send you a speaker gift this year. It's SEI golf balls. So you can display them. You can remember
I
the day you
golf.
spent with us. But you can give them
Well,
to somebody else.
I attempt to golf. So
Yeah, well, yeah, that's how I am too. Somebody on this call can probably attest to how bad I am. But um, upcoming in May, we are going to have our golf outing again. We have upcoming our cornhole tournament as well with the local Philadelphia schools. And then in October from HNTB, we're going to have Gregor Woolman join us in order to talk about a network tight arch design he did in about the mid 2000s. So thank you for joining us today. And thank you, Brandon, again. If you need anything, please reach out. See that there's PDHs in the chat. You can follow that link and then click on the link on our website and get the PDF for the PDH. So thank you very much, guys. I appreciate it. See ya.